All right, so the next thing that I want to look at after looking at the four different types of equations are geometric and exponential equations. I want to actually look at these in situations because they're very similar. And so as a mathematician, you're going to need to know when do I use one and when do I use the other. I mean, you have the same shape, they have similar formulas. So let's go ahead and explore what their differences are so that you know when to use which formula. Both of them have the same initial value. Both of them have common ratios. And the main difference here is that in the geometric sequence, you subtract 1 from the x value or the n value. So it actually can make quite a big difference in your results. So let's look at a problem. The first problem that I have is, which would you prefer? Being given $1 million or 1 penny the first day and double that penny the next day and then double the previous day's penny and so on for 1 month. So at first glance, we would think that $1 million would be a lot more, right? But if we use geometric sequences before we decide to see how the pennies add up, we might find something else. So we're going to start with a penny a day, and then we're doubling that amount for each day that follows and doubling the previous amount and so on. And we're going to continue to do that for 30 days. So how do I know if this is an exponential or a geometric formula? How do I know? Well, before we decide that, let's go ahead and find the common ratio. We know that both of these are going to have a common ratio, whether it's exponential or geometric. So I found out that my common ratio will be multiplied by 2. So my common ratio would be 2. So when I plug it into a formula, that's going to be my b variable. And then the next thing that we have to find is, what is the initial value? So on day 1, what do we start with? And that would, of course, be, we're going to start with 1 penny. And I'm going to go ahead and type the formulas for each one here. So exponential is a times b to the power of x. And then geometric is that cut off a little bit, so I'm going to say, and you write it on your paper, a times b to the power of x minus 1. So we already said my common ratio is b. And my initial value, or a, is going to be 1. That's the value of y when x is 1. And so I'm wondering, before I figure out what formula to use, is this exponential or geometric? Well, is this continuous or discrete? So remembering continuous, it keeps going, whereas discrete, your amounts are given for 1 item or 2 items. And then, of course, if you look at this, the problem tells us that it doubles on the day. So there's not a thing as like a day and a half. That doesn't exist in this particular problem. It only exists with 1 day, 2 days, and so on. So I'm going to go ahead and select my geometric sequence formula for this particular problem because it's discrete. So I'm going to go ahead and plug it in. I put in my common ratio there, as you can see, and my initial value. And I just always like to solve just in case. So I'm going to plug in on day 1 and then on day 2 just to make sure that I'm getting the right amounts. And so my formula, for example, for my day 30, to answer the question, right? How much money would I make on 30 days? That happens when f of 30, and when you plug it in, that's essentially going to give you 2 to the power of 29. And that, when you check in your calculator, is going to be, let me see real quick, 5,368,000. So it's actually better to get a penny a day. Here's another problem. A population of bacteria in a petri dish increases by a factor of 3 every 24 hours. Then the starting population is 1 million bacteria. So again, you have to figure out if the graph is going to be continuous or discrete. Are we talking about continuous or discrete variables here? When it comes to population growth, unlike money growth that you get at the end of the day, right? So in this, I'm going to go back to this example. There's not like 1 3/4 of a day interest. It only gives the interest on, or it only gains on day 1 or day 2. But in this situation, population increases, and it increases by a factor of 3 every 24 hours. So I'm going to make my table here, and I'm going to put my values in a table first. On the first day, the population is going to increase to 3 million. So my initial value is going to be 3 million. Second day to 9 million, and so on. So the question here, is it continuous or discrete? Is the population still growing every hour? When it comes to bacteria, you know your answer from science, of course, that it is still growing. I made a mistake earlier when I said on the first day, it's actually, you start with 1 million, and on the first day is 3 million, and then the second day is 9 million. So when I think of what the common ratio here is, they tell you that it's a factor of 3. So you're multiplying whatever you had the day before by 3. So your common ratio is going to be 3. We already answered the question of whether or not this is continuous or discrete. This is, of course, continuous. Your bacteria is going to keep growing every hour. So we don't have to wait for the 24-hour period as we did in the previous problem. So now that we have identified that it is exponential, we're going to use that formula. I already have A. My initial is 1 million. B, my common ratio is 3. And I just plug it in. A times B to the power of X. So Y equals 1 million times 3 to the power of X. And of course, because this is a function, you would probably want to write it in function notation, so f of x. I always like to plug in some x values just to double check my work and make sure I have it correctly. So let's say for 3 24-hour periods, f of 3, what would I get? That would be 3 to the power 3. F of 6, 3 to the power 6. You can do the math on your calculator. This is the graph for both of these situations, basically. We have the population on your left of the bacteria, the one that we just did in millions. You can see how the graph is a little curve. And on the right, we have the geometric sequence. And you can see how because it is discrete and not continuous, we have it as a bar graph. But if you were to draw the lines, if these were scatter points and you wanted to draw, it would look like a similar curve. But this is what the graphs would look like, basically between continuous and discrete. And again, the main difference is the formulas. The exponent from the geometric sequence is going to change a little bit. We're going to subtract 1 from that, whereas the exponential function is just to the power of x.